Good afternoon, class. In today's video, what I wanted to do is to go over how to get the general result for energy during in our series of relativistic energy videos. So in the last few videos, we've done E equals mc squared, we've done relativistic momentum, and in the last video, we talked about E equals momentum times speed of light, which is E equals pc. So in this case, what I'm going to do here is I want to get the general result. I want to include everything with mass. I want to include everything without mass. In order to get that, I need to start with this, and hopefully by the end of all of the algebra that I'll be doing here, I will end with this same equation, because that will have shown that the general result actually works, especially in the special cases. So here we go. Because we're talking about relativistic energies, we're going to start with relativistic momentum. So we're going to recall that P equals mu over square root of 1 minus u squared over c squared. So what I'm going to do is I'm going to plug this in. I'm going to basically multiply both sides of the equation by c to get our energy ID, to get the energy term. So I've got Pc equals mu c over square root of 1 minus u squared over c squared. But as you can see, I've already got this square root in here, and I don't really want the square root. So what I'm going to do is I'm going to square both sides of the equation, which is exactly what I did here. That allows me to get rid of that square root sign, because it's a little bit more complex if I have to deal with square roots in the mix. So I've got p squared c squared equals m squared u squared c squared over 1 minus u squared over c squared. Now, don't get me wrong, this looks like a mess. I understand that. But there is something that I'm noticing, and that I've got this u squared over c squared term, and I have a u squared in the numerator. And so the mathematician in me starts thinking, I wonder if I could take that and cancel, and because I could do something with this denominator, but this denominator, for all intents and purposes, is pretty ugly. I don't really want to deal with it. But what if I could cancel it out? And that's exactly what I'm going to do, using one of the great mathematical tricks of adding by zero. So before, we would always be taught multiply by 1. If you don't want to do anything to the other side of the equation, if I wanted to do something, maybe I'd say I'm going to multiply it by 2 over 2, and that will give me a good result. Perfect. But we can also add by 0, and that's actually another really cool trick that we can use in our mathematical bag of tricks. So when I look at this, I say, this is I could probably get this u squared over c squared. So I'll factor out an extra c squared. So I got m squared c to the fourth u squared over c squared. Now, if I could just subtract 1 from it, that would be awesome. But you can't subtract 1. You can only add 0 if you don't want to change what's on the other side of the equation. So in order to do that, I want to subtract 1 over here to be able to cancel this stuff out, these two terms out. But in order to do that, I have to add 1 on this side, which is, of course, being multiplied by m squared c to the fourth over 1 minus u squared over c squared. So I have that. Now, of course, this is order matters, so this is actually the negative form of this term. So that's why in the next step I have this minus sign, because these two terms have canceled, and so I've got minus m squared c to the fourth. Now notice, all of this is this is all rest masses right here. However, now that I've got this m squared c to the fourth over 1 minus u squared over c squared, that looks like this 1 over 1 minus u squared over c squared, that looks like gamma squared, which means that I've got a relativistic mass here, so m prime times c squared quantity squared minus mc rest mass m c squared times quantity squared equals p squared c squared. Now, not gonna lie, I squared all of this to make things look nice, but I kind of got to get rid of this, because why do we want p squared and c squared? But we have to recognize that E is equal to, we're talking about relativistic energy. We have to have the relativistic energy is equivalent to the relativistic mass times c squared. So if that's the case, then I can actually change this one to E squared. So I've got E squared equals PC quantity squared plus MC squared quantity squared. And of course, I don't like that. I'd rather have just the regular E. So in this case, E equals the square root of p squared c squared plus, m squared c to the fourth, or mc squared quantity squared. However, one of the nice results of this is that if your mass is 0 kilograms, like a photon, then your energy is equal to just Pc, which is exactly what we got from the beginning, which we argued from conceptually in the last video. So therefore, we've got a general idea. So if you're moving, you've got your rest energy. If you've got mass, you have this kind of energy. If you don't have mass, you have this kind of energy. So we have the full spectrum of ways to get energy out relativistically, either if you have mass or you don't have mass. So that concludes this video on relativistic energy. Good luck in your studies. May the force be with you.